Ian Brevard, Shinya Katsumata, and Dominique Orchard about combining effect and coeffects. So as the title says, the idea of this work is to put together two lines of work about effect and coeffects. So the idea of effect system dates back to the 80s, and there has been a lot of work trying to formalize the idea that we can describe impure computation by effect system. And at the same time, trying to enforce the correctness of impure computation by means of this effect. And usually this is done by using some kind of program analysis. I put here some work that are not the only one in the direction of effect system, but they are the one that inspire our work. In particular, we will use the idea of parametric effect monad as used by Katsumata. And on the other hand, there has been some recent work about coeffects. These are certainly less known. And the idea of coeffect doesn't start with the name coeffect, but dates back to previous work on context-dependent computation. For instance, Tarmo, that is in the room, has done some work that inspired our work on coeffects. And more recently, what we observe is that this idea of context-dependent computation is very related also to the line of work on resource type system and substructural type system. And so the research question we are trying to address is how we can combine these two lines of research. So in my talk, I will use the word effect and coeffect, but what I'm thinking about is as them as types, so some type information that represent effect and coeffect. In particular, we would like to have properties like we usually have with types, where if a program is typable, then we can ensure some property of the program, like it cannot go wrong. But the difference with respect to usual type system is that now we want a way to describe or characterize a property about the way the program interacts with its environment. And this is my way of thinking to effect and coeffects. They are both descriptions of intentional aspect of program behavior. And they are, in my view, two sides of the same coin, in the sense that effect describe the way that a program influences its environment, while coeffect are some kind of a requirement of a program with respect to its environment. And in our work, we would like to put these together and make them interact in such a way that we can have a way to describe how a program influences its environment, but at the same time also express the requirement of the program on the environment. To establish this interaction, what we will use is a well-known correspondence between effect and monads and coeffect and comonads. And we will use a tool to make monad and comonad interact. People have looked into this much before us. And this is the idea of using some kind of distributive law. So we will communicate effect and coeffect system via this distributive law. All right. So here a bit of the menu for today. I will start to make more precise what I mean by effect system, and in particular, I will present what we call effect-graded monad and the corresponding coeffect graded monad, and then I will show how just by putting them aside, we can just have a system that where they coexist, but then more interesting, I will show how we can make them interact by using the distributive law. All right. So monads are nowadays used everywhere, so I don't think I need really to explain you what a monad is, but let's have a look at a simple example that I will use later in my talk. So let's consider a writer monad. We can model writing to an output with a monad in a pure functional language, where, for instance, we can add a primitive print that takes a string and return a monadic type that I denote T of the unit type. And we can use this operation to print to an output and by composing the monad, we can obviously print several times to the output, and we can obtain a computation that overall has a monadic type. I will use in my talk the let notation, even if maybe some of you are more familiar with the do notation, but the point is the same. What is important is that by the let, I will denote the composition of monad. Okay, so these are monad like you can use in Haskell, but what we want is to talk about effect, using monad to talk about effects. And in particular, as I said, there has been a lot of work on effect system dating back to the 80s. And in general, if you look at effect system, the idea is that we have an inference system assigning to a program not only a type, but also an effect. And usually in the first work on effect system, this effect is a global property about our program. But more recently, some work has shown that we can, in fact, put together monad and this effect system by having an effect-graded monad. An effect-graded monad is a monad that I write with this notation T with a subscript E, where E is an effect, which is an inhabitant of a formal language that is given by a preorder monoid. The idea is to put together these monad and effect so that we can use the operation of the monad to introduce effect and to compose them. And the reason why the effect language is a preorder monoid comes from the rule of the monad. Indeed, the return of the monad introduces a unit, the unit of the monoid, while the composition of the monad corresponds to the multiplication of the monoid. Okay, so let's go, yes?
Can I ask, is the preorder monoid ever not a family of sets with union?
Yes.
Okay.
Let me give an example where we go back to the example I gave before of the writer monad. And now we can take as a monoid a finite sequence of the symbol P. Sorry, let's take mainly a starting symbol P that denotes print, and I take word on this single element. Okay, it's a very simple monoid. The unit of the monoid is just the empty string, and the operation of the monoid is just concatenation of a word. Okay, and we can use this family of effect to collect information about performing a print operation. And we can do this by decorating the type of print now with a symbol P. So that when, for instance, we go back to the example I gave before and we perform multiple print, each time we will introduce a new P. And by the composition of the monad, we will collect all of them. So in this case, since I perform 3 prints, I will have an effect-graded monad where the effect is 3 times P. By the way, I forgot to say something before. I used the word effect-graded monad to distinguish from previous work that has used the word parameterize, indexed, parameterize effect. So we would like to try to distinguish our work from the previous work, but at the same time, ideas like this have appeared everywhere. So we believe that there is a general pattern behind the idea of parameterizing in some way or indexing in some way monad with effects. Okay, but let me continue with a slightly more interesting example before passing to comonad and coeffect. So let's consider now a monad representing a single cell state where we have 2 operations, get and put, on this single cell, where we can get the content and we can write something in the cell. Now again, we can use another monoid, this time with 2 basic elements, P and G, standing for put and get, and again we can collect the information of which operation we are applying. So in particular, if we use this information in a combined program that performs a get, a put, and a get, what we will obtain is this information in the monad. Now, we can wonder if this is useful because it seems quite simple, but you can think that having this information just from the type can be useful to make sure that everything goes well, that we cannot go wrong. Because, for instance, in this example, we need that the cell is already set to some values. Otherwise, the first get would fail. So we can do some analysis then on the type instead of on the program. All right. Sure.
What if you have a conditional, say, if true, do a get, else?
Yes, this is a very good question, and for the moment we don't deal with this case, but there are ways to deal with case like this. For instance, by using some kind of dependent type, and I will comment on this at the end. It's the same for conditional or for some kind of loop or recursion, obviously. Okay, so let me instead go into coeffect, and let me try to give you an idea of coeffect-graded comonad. So comonad are much less popular than monads, and the reason I think is that we don't understand the concept yet very well. We don't understand how we can describe computation via comonad. I'm not talking for everybody, but at least I'm talking for myself. But there is an example that I understand quite well about comonad, and is an example coming from linear types. Indeed, the exponential modality bang of linear types or linear logic is a comonad. And how can we use this comonad? In general, this is used to describe different functions based on their behavior. For instance, we can distinguish functions that use their argument once from functions that they use their argument 0 or multiple times, like in the example I gave here. So the comonadic structure of the bang modality comes from some of the law of linear logic or of linear types. In particular, the co-unit is what is usually called the reliction in the linear logic literature, while the co-multiplication of the comonad is what usually is called digging. So you can see that if you reverse the arrow and you call this T, what you obtain are the rule, the unit and the multiplication for a monad. But here the important part is that this is a comonad, but not only a comonad, but it has some additional structure that is what give the usual substructural flavor of linear logic. And this that the bang is a comonad, but it has also the structure of a comonoid, where the comonoid laws correspond to weakening and contraction of the bang. Okay, now we want to do the same we did before with the monad and introduce some operation. And here is where I ask you to give me some trust. Okay, because I will not spell out all the details. So let's assume that the underlying language that we have of linear types is a call by name language. So in particular, we have our weakening and contraction, but they work call by name. And now I would like to add another primitive that I call ghost for some ghost code. The idea of this ghost code is that I want to execute it, but then I just want to erase the result. I don't want to use it. This is the assumption I'm using here is that the language is called by name, because otherwise this would be exactly like the weakening, because the weakening directly erases the result. Okay, so if I add this primitive, I can give it a type like the following, where I mark that the result as a type bang, because now I can erase it. I want to erase it. The semantics tell me that I will erase it. So it is sound for linear logic to add this operation with this type for linear types. Now we can use this operation in programs, and we can mark with this ghost some code that we want to use, but we will erase. As you see, the result of ghost is passed to the variable x, then we erase. Okay. Now, I will try to make clear later why this why this operation is give us an intuitive example. But let's see what are coeffect systems. So far I presented the comonad, but in general I said we are interested in coeffect system. And likewise, effect system, the idea of coeffect system is to have an inference system, a formal system where we can derive judgments for program, where now we have information of type, but also information about coeffect. And usually, the way of looking at this information is as properties of the environment. So I mark, as in linear logic, this coeffect system with the bang, but now this bang it has a subscript that is the coeffect. And this coeffect, instead of being a monoid like in the case of monad, now is a preorder semiring. So we don't have only a multiplication, but we have also an addition of the semiring. And like in the case of the monad, this operation comes from the rule of the co-unit and from the rule of composition. In particular, the co-unit give the multiplicative unit, while the composition use both the operation of sum and product. So let me try to read this rule. This rule says that if we want to compose a computation E1 with a computation E2 on the variable x that has the coeffect R, then we need to multiply the coeffect in the context of E1 by R and sum them to the context of E2, where by multiplying and summing, I'm talking about the lifting of the operation of the semiring to the context. So in particular, sum over the context is sum in the element of the semiring, and multiplication over the context is the multiplication of the element of the semiring. Okay, so this is the idea of coeffect, but let's see how we can use it for the example I gave you before. So we can take a very simple semiring that now has only one inhabitant, that is an absorbing element D. Or better, it has only one distinguished element D that is an absorbing element. And this stands for dead. I want to do some kind of liveness analysis where I mark by D the code that is not accessible. Now, the primitive I gave you before introduced this D. So in particular, I will mark both the right-hand side and the left-hand side with this D. And remember that is absorbing, so no matter what is in G, now everything becomes D. So in the example before, I can mark Z with this D. And I can go a bit further and use another element for denote live variables. And for instance, I can denote Y in this example as live. So in particular, I can perform an analysis where I can track live variable and dead variable. Okay, let's see another example. This example is due to Thermo, and it is an example of stream computation. In particular, we can think about stream computation as a context-dependent computation, where, for instance, we have some element that represent a synchronous stream, and we have an operation read for reading from this stream. Now we can design a coeffect system by using a semiring that is the Arctic semiring. The Arctic semiring is obtained by taking the natural numbers plus a distinguished element minus infinity, and taking as operation max and plus, where the plus now is the multiplication of the semiring. So even if I denote it with the same symbol, now it takes the role of the multiplication. And now we can use this semiring to count the number of times we perform a read by just giving the type bang1 to the read operation. And this typing rule for read. Now, by looking at the composition, again, since we are composing by means of the multiplication, and in this case the multiplication is plus, we can count the number of times every read is performed. Yes?
It should be minus. So what is minus infinity? What does it mean that I read, at most minus infinity characters?
No, minus infinity means that I don't have information, mainly. Okay, so now I gave effect-graded monad and coeffect-graded comonad, and I want to put them together. So we want, going back to what we said before, we want them to interact, but now we will make them interact in the version I gave here. So we will make interact effect-graded monad and coeffect-graded comonad by using an effect-coeffect-graded distributive law. Let's take another example that put together the two examples I gave for effect and for coeffect. Let's consider a program that has some ghost value and then perform the free print we did before. But now in the ghost value, in the ghost code, I put a print. So So now the question is, which type shall we assign to this program? Shall we assign a monad that count 3 times the print, or shall we assign a monad that count 4 times the print? Obviously, there is no real answer to this, because we can write our program in a way that we just perform 3 times, or in a way that we perform 4 times the print. And this is the reason why I put this semicolon as composition instead of putting other things. Let's see the way to achieve the first type. So let's look at the type of this ghost code. So this ghost code perform a printing, but this printing is inside the ghost. So this term is type bang D because it's dead code. So a first way to use it is just by using the construction we already have and interpreting this D just as a kind of weakening, so just by using the let composition for the bang. And this will not, even if we'll execute the effect, it will not track it, because the type system doesn't know that we want to track it. It just performs the code that is inside the ghost and then erase it. So this is the first way. But then we have another way to make them interact. That is by the distributive law. And the distributive law is what can make the bang and the T communicate, because now it performs an exchange of the bang and the T. So for instance, now we can write another program where I use the other let. That's why I denote it by let T, the let of the monad, and I use the distributive law. And this is what we can use to achieve the type with 4D. And the way we can do this is by using a decoration for the distributive law, where we introduce these 2 operations, I and K. The first that take a coeffect and an effect and return a coeffect, and the second that takes a coeffect and an effect and return an effect. But let me give you an example of how we can use it concretely. Now, the type of the term after the distributive law has this tk of p. And depending on how we set this operation, we can achieve both the case where we have 4 times p or the case where we have 3 times p. And this is all in the way we define this operation. These operations are something that we have already seen in the literature. Actually, Tarmo suggested that is related to the Zappa-Szép product. And it has a bunch of axioms that I will not give here. I will not describe, sorry. That I'm giving here, but I will not describe in detail. But the idea is that they have to reflect some structure of the computation, but then we still can pick different effect-coeffect operation. All right, so what I presented is a system where we can put together a preorder monoid of effect, a preorder semi-ring of coeffect, and grade the monad with the first and the comonad with the second. And then we can make them communicate with a matched pair of operation I and K. And we can grade the distributive law by this I and K. Now, you may wonder why this is okay, putting all together, because in the end, what matters for us is that the equational theory that we achieve is meaningful. And to show that is meaningful, this equational theory, we show that this equational theory preserves types, but also that it has a well-established denotational semantics. And with this, I'm done.
So I think we have one quick question. Anyone have a question?
There seems to be there's a lack of symmetry between the effect and the coeffects. So you have the monoid on one side, but then a semi-ring on the other.
Yes.
Can you explain the genesis?
Yeah, so the reason why, the intuitive reason why you have a semi-ring on the coeffect side is that mainly the coeffect is something that describes context-dependent computation, and in particular, we are dealing with an environment where we have multiple assumptions. So we have multiple variables, and the idea of this plus operation is that we want to deal with each variable individually. While in the effect case, what we are interested is more in the global property of the computation, and so is more on the right-hand side of the typing judgment, where you have only one conclusion. One can think to generalize this to a classical logic-like system where it has multiple conclusions also on the right-hand side, and there maybe another operation will come out.